All right, before we go into fracture mechanics, let's model the wind turbine. We started in the last class. So please open Abaqus. Please open Abaqus CAE. So we're modeling three blades of wind turbine without the tower. So we'll quickly do that and go to fracture mechanics. So we'll be taking one of this wind turbine blade and seeing where the crack develops. But first we'll model these three blades, and then the fracture mechanics concept we'll learn on tensile testing. And after that, we'll come to the maybe on Wednesday's class, we'll do the fracture mechanics on the wind turbine blade. So today we'll do just the modeling of wind turbine blade. So open Abaqus CAE. With standard or explicit model. So everyone has Abaqus open. All right, I quickly, in 10 minutes, I've created the wind turbine blade. So I'm going to follow the same procedure. All right, so first create a part. So in the part module, create part, solid extrusion, size 2 meters. I'm planning to enter everything in meters. So this is a meter from our fingertip to the elbow. That's 1 meter. So 2 meters I'm giving. So that's the maximum distance here. This would probably be 2 meters, and this vertical distance would be smaller than 2. So draw a rectangle. Give the dimensions as say 1 meter. Horizontal distance is 1 meter. And the vertical distance is say 0.4. So usually the wind turbine blades are pretty long. We consider some arbitrary size here. So let me change the font size. So I've drawn a rectangle. Length is 1 meter, height is 0.4 meters. So as you have observed last time, I've used loft option. So if I'm planning to loft from one plane to another, I need to be careful with the origin. So we'll create origin. So select a construction line, a vertical construction line. So look for a construction line. If you place your mouse, it says construction line. Hold on with your left mouse and select the vertical and type in, when it's asking for X, Y, type in 0, 0. And that places the vertical line at 0, 0. Do the same for horizontal construction line. So hold on to the construction line, select the horizontal construction line, and type 0, 0 in your X, Y and escape out of it. So that's my origin actually. My rectangle is not actually centered. No problem so far. Rectangle 1 by 0.4. And I have a horizontal construction line and a vertical construction line. So we're going to make this rectangle center to be exactly origin. And the way to do that is through relations. So look for the relations, add constraint. So you would see it as triangle equal to with those signs. So select the constraint option. First fix the horizontal and vertical construction lines. So select fix and select the horizontal construction line. Say done. And then select the vertical construction line and say done. So when you do that, it turns into green color and it puts the triangles there, saying it is fixed. And now apply the symmetry constraint. No problem so far. Apply the symmetry constraint. Select the axis of symmetry. So select the horizontal axis, horizontal construction line you created. Then select the first entity for the symmetry constraint. Select the top horizontal line and select the second entity for symmetry constraint. Select the bottom horizontal line. The rectangle will move so that horizontally now it is symmetric. So do the same, select the symmetry again, click on symmetry again. Select the axis of symmetry, select the vertical construction line. Then first entity for symmetry, select the left vertical line. Select the second entity for symmetry, select the second vertical line. Now the rectangle will turn into green. Everything's defined. And it is the center of that rectangle is the origin. It's important to do that because the next steps onwards, I'll be creating the same sketch again, and the origin will be my reference for all the sketches I'm going to put in the different planes. Everyone's able to do that? Do you have the rectangle in green? Okay, so before we say done, we'll save this sketch and we'll bring it back again on a different data plane. So the way to save the sketch is, you would see the floppy disk icon. So this is the floppy disk icon, save sketch as. So click on save sketch as, save it as sketch 1. And when you enter, it would have gone. In the trees, it says sketches of 1. That's where it has gone. We'll go and bring it in when we need it. It's right now there at the bottom of the tree. We'll complete with this operation of extruding the rectangle. So say done. And extrude it by say 0.2. It was offering 0.2 and I'll select 0.2. So it's just a rectangular block. One by 0.4 by the Z direction, it was 0.2. So I haven't set the work directory, so make sure, go to file, set work directory. So select the folder icon and create a folder. So create new directory. Look for the folder icon at the top. Call it turbine blades, turbine_blades. Okay. And select the folder and say OK. So it's saving in C temp turbine blades. That's my folder. There's the working directory. Say OK. And now save the CAE. So it should save in the turbine blades folder. So turbine underscore blades. So we'll be using the same one of the turbine blades for our fracture analysis. So that's just the rectangular block. No problems with saving the file. You are able to set the work directory. Yes, Alex.
Correct.
If you go to file set work directory again, it will say the work directory, no? Or go to your temp folder. So if you go to temp folder, you should see the CAE file saved now. Temp folder and the name you have given. So that's the turbine blades.cae.
Okay.
So that's the rectangular block. So I'm planning to create a rectangular cross section at various planes along the length of the wind turbine and loft between the planes. So to create more planes, I would create datum planes tools, datum, and I'll offset from the already existing face of rectangle. So go to tools, datum, plane, offset from plane. So tools, datum, plane, offset from plane, and select the rectangular face. Enter value. So at the bottom you have an option to choose either enter value or select point. Let's choose enter value. And the arrow is pointing in the positive Z direction. Otherwise flip, make sure it's pointing in the positive Z direction. Say OK. And enter a distance of say 1.5 meters. And now if you zoom to fit, at the top you have zoom to fit, you would see the datum plane created far away from the initial rectangle. No problem so far. So let's create the rectangle again, rectangular cross section again on this datum plane. So the third option on your panel, it says create wire planar. So we'll create a wire planar on this datum plane. So create wire planar, select the datum plane. And when it asks for select an edge or axis, that will appear. So you can select the rectangle's vertical edge at the back. It will go into the sketch mode. It goes vertically. It goes normal to that datum plane. You're in the sketch mode now. You want me to repeat it? So I'll go back. I'll cancel this. So if you have the datum plane, we're going to draw on this plane. So we're going to create a wire planar. So select create wire planar. It's asking for a plane for the planar wire. So select the newly created datum plane. It's asking for select an edge or axis that will appear. So select the vertical edge of your rectangular block. It goes into the sketch mode and you'll be taken normal to the datum plane. And I can create the rectangle again, but I have saved it as a sketch. I can bring it using the add sketch option. So the add sketch, you already saved that sketch. So say OK. It's tentatively placed it on top of the rectangle, but it's asking me to, do you want to translate, rotate, mirror, scale? I want to scale. The wind turbine blade cross section reduces throughout the length. The cross section reduces. So I'm going to say scale. Scale about the origin point x comma y is 0 comma 0. You want me to repeat? Anyone? Okay, I'll cancel this. Cancel. So wire planar, create wire planar, select the datum plane, select the axis that, and you go into the sketch mode. So choose the folder icon. Instead of floppy disk, right beside that, you have an open folder, add sketch. If you place your mouse, it says add sketch. And that's the only sketch we have. We created a rectangle. Yes, Alex. So probably you didn't save it. So let's do one thing. So cancel out of the procedure. Uncollapse the parts from your tree. Uncollapse part 1. Uncollapse features. Uncollapse solid extrude. Section sketch. Right click on it, edit. So it'll be taken into the previous sketch. So click on the floppy disk icon, save sketch as, and give the name here, sketch 1, and say done. And come out of this, say done. You don't have to change anything. So now when you go to the create planar, create wire planar, and select this datum plane, and select the vertical axis. And now when you ask to bring in the sketch, add sketch, you should see the sketch 1. Okay. Say okay. So I don't want to say done. If I say done, the cross section will not change at all. I want to reduce the cross section. So click on scale. X comma y is 0 comma 0. So that's why I was careful. The center. So I'm going to scale about the origin point. So uniformly I'm scaling. Enter. Scale factor. Instead of 1, I'll reduce it to 50%, which is 0.5. So when I say 0.5 and enter, your rectangle now has the length of 0.5 and the height of 0.2, exactly half of the previous values. Don't say done yet. We'll also rotate it. So the cross section will reduce, and also the rotate blade usually is twisted throughout the length so that it can, wind can rotate it. If from any direction, if the wind blows, it can rotate it. So after you scaled it, rotate. Center is again 0 comma 0. Center for rotation again is 0 comma 0. Enter. Angle of rotation, let's give 30 degrees. So if I give positive values, it rotates in anti-clockwise. No? So I'm expecting it to rotate in anti-clockwise. If I give negative value, it will go in clockwise. So angle of rotation 30, enter, and say done. And say done. So that's what you did. You created a smaller rectangular cross section on the datum plane, and it's also rotated at the same time. So is that okay? Are you able to see the rectangle on the datum plane? We'll repeat it again. So we'll create another datum plane again. So go to tools, datum. Frank, I will email you this so you can also work together. I haven't saved it. One second. Okay. So please download it, place it in the temp drive. And so place it in temp drive. We are not running this anyway. We'll just create the model and we'll come back to it probably on Wednesday or maybe Monday's class. Most probably Wednesday's class, we can come back to this file. Were you able to download, Frank? All right. You have Abaqus open. Okay, so go to Tools, Datum, Plane, Offset from Plane. Now select the newly created plane. So I selected this datum plane, enter value. The direction is pointing in the positive Z direction. That's fine for me. Say OK. And say this time the offset distance is 1 meter. Enter. So it created another plane. So if you zoom to fit, so which is auto fit at the top. That's the third plane I created. Are you able to do that? All right, so go to create wire planer. We'll repeat the same steps. So create wire planer. It's asking for a plane to sketch 1 meter is the distance I have given. So when it's asking for a plane, select the newly created datum plane. Select an edge or axis that will appear. I'll select the rectangle at the back, the vertical edge of the rectangle here. It goes into normal to that newly created plane. Again, we'll add the sketch, add sketch from the bottom, or you could draw the rectangle here itself, center it with the origin and again rotate it, but it saves us few steps. So add sketch, bring in the sketch, sketch 1, okay. And it is of the previous, so let's scale it, scale about origin 0, 0. Let's scale it to 25%, 0.25. Okay, you want me to repeat it? So when you add in the sketch, it asks you to scale. So choose scale option, enter origin 0, 0, then scale factor of 25%, which is 0.25, enter. So it will become a small rectangle and rotate. Before you say done, rotate. Again, the center point for rotation is 0, 0. Enter. Angle of rotation, this time let's rotate 45 degrees. Previously we rotated to 30. So in the same direction, I'm entering positive value. So 45. So previously the rectangle was 30. Here it's 45. And say done. And done again. You want me to repeat it? Quinn? Let me know. I'll come and help you out. If anyone needs help.
Oh, actually, I'm not.
Can you say that again?
My first one is like not in the center. It's like off the side. I think my second one is too.
Okay, that's fine. We will see if loft is a problem.
Okay.
We will come and fix it. All right. So once you have, you need actually more than this. I just gave at three locations. I gave the cross section, and they are rotated also. So going to loft, go to shape, solid, loft, shape, solid, loft. And we need to fill in this window. We need to select the 3 cross sections. And the way to do that is insert before, insert after, those things are there, or you can delete. say I'm using the insert before. So insert before and draw a box around the latest rectangle that you created. So this rectangle, I've drawn a box around it and say done. So again, go to insert before. So to the right, you have insert before. Anyone wants me to repeat? Anyone wants me to repeat? So go to insert before, draw a box around the middle rectangle and say done. So for the first two, it's fine whether you use insert before or insert after. But the third one, you need to be careful because they have to be in the same order. The middle one has to be in the middle. So choose section 2 and say insert before. If you inserted in between section 1 and section 2, it won't do the loft. So they have to be in the same order. Loft can't change directions. It has to go in the same direction. So choose section 2, insert before, and maybe you can change this to wireframe mode so that you don't select faces. So render model wireframe. So render model wireframe is at the top, and carefully select the front edges. So hold on to the shift key and select the front edges of the rectangle and say done. So the only care I had taken was when I was filling this, section 2 was in the middle. I could have started with the first rectangle and gone to the last rectangle. I have to just make sure section 2 is in the middle, otherwise it can't change direction, the loft. Yes.
That is the stages do not form a close loop.
Is it? We'll see. Make sure you have section 2 in the middle, Frank.
Oh, very good.
So that's the common mistake. You can't change direction. So right now it's doing section 3, section 2, section 1 in this direction or in this direction. So this has to be in the middle, otherwise it will not. So once you say OK, so it should complete it, and you can change from wireframe mode to shaded mode. So go back to your shaded mode, and you would see the rectangular cross section decreasing, and also it's twisting as the length is varying. Anyone had any trouble? I'll come and help you out. Quinn, was it able to do loft?
Yeah.
You have still the same problem?
Yeah. Like you said,
So you forgot to select one more here.
you can use this one.
Yeah, so go back to, yeah, so yes. So section 1. Yeah, now it will do it. Okay. Right?
Oh, okay.
So it can't be open section, so make sure you're selecting all the 4 edges of the rectangle. Anyone had any trouble? Quinn?
We're figuring it out. It's not good enough.
I can help you out. Say, let's easy way. So it's good to get problems so that we can fix it. So the ones who had trouble, go to your part, Quinn. I'll help you out to fix it quickly. So go to your tree, uncollapse the parts. Whichever one is problematic for you, say wire 1. In your case, maybe wire 2. Go to that section sketch, right click and say edit. Were you able to do that?
Yeah, I have that.
Edited the sketch. So now select the translate option. So you have translate option here. Draw a box. So it says select the type of translation operation. Say move. Draw a box around everything. And say done. it asks pick a start position for translation and go in and pick the center of your or the intersection of the two lines, pick that point. And when it asks pick endpoint for translation, enter 0, 0 here. And that should place it exactly in the center.
All right, I did.
Okay, so do that for other cross sections also. Say done. Whichever cross sections you think are not centered. So go to that wireframe mode in your tree. Right click on section sketch, edit, translate, draw, say, ask it to move. If you want to keep a copy, that's the option there. We don't want to keep a copy, so move. Draw a box around everything. Say done. And start point, select the intersection of the two construction lines. And when it asks for end point, select the starting point is this intersection. And when it says pick an end point, enter 0, 0 and say done. Enter, it will, this point will go, entire thing will move to 0, 0 now. Did that work for you?
Maybe.
Now try lofting. Once you have all the three sections centered. Try lofting. Solid, loft. Insert before. Okay, draw a box around it. Insert before. No, careful. Go back. So select section 2. Insert before. Yeah. Okay. So go back to your shaded mode from wireframe mode. Anyone else had any problems? Is that good? It's good to get problems, so you will know more about Abaqus. All right, so usually the wind turbine has a hub region. It's called nacelle. All the electronics are placed inside this nacelle. So this is your blade, and that's called nacelle. All the electronics will be mounted there. So we need to create a, so the part is not done. We'll create a hub region or a nacelle region, and then we will do rotating pattern to get the two other blades. So to do that, again, go to shape, solid, extrude, shape, solid, extrude, and select this side face of the rectangle. So that's the very first rectangle I have extruded. The side face I have selected. So shape, solid, extrude, select the face of the rectangle. And when it asks select an edge or axis that will appear, select the vertical edge. And you will go into the sketch mode. So I'm going to draw a circle and I'm going to extrude it in the direction. That's the plan. That's going to look like nacelle. You're back in the sketch mode. I'll repeat it again. Cancel. So I'm going to do that again. So XYZ. So if at all you don't see these views, that's usually a problem. Abaqus, I don't know why it removes it. If you don't see these views here, go to view, toolbars, make sure the views is check marked, and then drag it to one of the panels. It will attach itself, and that's the isometric front view and so on. So go to shape, solid, extrude, select the side face of the first rectangle we have drawn. Select an edge or axis that will appear. And it should go into the sketch mode. Choose the circle option. So center outside don't put the center on the rectangle, center outside, and draw a big circle. We'll give constraints and we'll dimension. So just draw a circle with center outside the rectangular face. So let me change the font size. You don't have to do this. If at all you have a problem with font size, so select the sketcher options, dimensions, and give a big value here. You won't have the problem. It's only for the podium computer that's a problem. So give a radius. So use add dimension. So select the circle and say give a radius of say 0.2. I gave a radius of 0.2. No, select the arc. So I'll do that again, Control Z. Say add dimension. Select the arc, not the center point. Just click on the arc, drag your arrow, place it somewhere, and give some radius, 0.2. Or I'll give a slightly bigger radius. I'll change edit dimension value and I'll change this to 0.25. And say OK. So my center is still outside. I need a hollow section, right? So that's why I placed it. But we'll add constraints. So I gave a radius of 0.25. So that's how I edited the dimension. You have a way to edit the dimension, edit dimension value, and click on the dimension, and it changes it to whatever value you need. So we'll add constraint. So add constraint. Let's say coincident. Select the circle, select the arc of the circle, and select the endpoint of the rectangle. So then the circle passes through that endpoint. Do that again. Select the arc and select the endpoint. So your circle will be in green now. The radius is 0.25 and it's passing through the end corners of the rectangle. Everyone's able to do that? So let's draw one more circle. It's a hollow region, right? If I extrude just this circle, it will be a solid circle, right? It will be solid, it won't be hollow if I extrude this. So I need to draw one more inner circle. So create circle again. This time pick the center point, the previous center point. So we're drawing a coaxial or concentric circles. So select the center point and draw some circle of some radius and add dimension from the panel and select that arc and say let's say 0.1. I'm not sure, I gave some random values there. No one's able to do that. Now if you extrude, you will have a hollow region. This 0.1 is the hollow region. That's where electrons will go in. Say done. So it should exit out of the sketch mode, and it's asking you to extrude. If the arrow is pointing in this direction, which is positive x direction, flip the arrow. You want it to go the other direction. And the way to flip the arrow is beside extrude direction, you have an arrow. So flip the direction in case it's pointing in the positive x direction. You want it to go in this direction. And the extrusion depth, I think it's 1, right? The initial rectangle length we gave. So this rectangle length was 1 meter. So throughout that 1 meter, we'll have this hollow hub or nacelle. So depth of 1 meter, extrusion direction is going inwards, and say OK. And that should create the nacelle region. Everyone's able to do that? All right, that's all that we need for the part. we can create the other two blades by using radial patterns. All right, let's go to assembly mode. We have a radial pattern in the assembly. So go to assembly, create instance. So your assembly, there's nothing here. Only when you create instance and bring in the part. So that's one blade you have. Everyone has the part in assembly. Are you able to see it in the viewport? So let's create an axis for radial pattern. We need an axis, right? So let's create an axis for the cylinder. That itself will serve as the center for radial rotation, radial patterning. So go to tools, datum, axis. Select the axis of cylinder. So datum, axis of cylinder. Zoom in and select the hollow portion of the cylinder, and it will place the construction or the axis of cylinder there. So select the circular or cylindrical surface, and it places the axis. And we're going to do radial pattern now. No problem so far. So radial pattern is the second icon there in assembly. Just below the create instance, you have radial pattern. Select the radial pattern option. Select the instances to pattern. Just click on the one instance you have. Say done. And it does some crazy thing like this. The reason is it's not able to realize it has to use that axis as the axis for the radial pattern. So the way to change it is, so you have an arrow, select axis, there is a pointer, click on it where it says select axis and pick the axis you just created. So click the select axis, zoom in and select the axis of the cylinder you created, and it now changes to, now it is doing radial pattern about that axis you created. It's doing it only for 90 degrees. I want it to do for 360 degrees. And I don't need 4 blades. I just need 3 blades. Usually the turbines have wind turbines, so there are only 3 blades. And say okay. And you won't see any of this if the preview is switched off. So make sure the preview is on, otherwise you will not know the end product. And say okay. So that's your wind turbine blades, of course, without the tower. No problem so far. And if you, it's still not a single component. So if you go to assembly, uncollapse your assembly, uncollapse instances, you would see that 3 individual blades. If at all I have to merge, we'll anyway be doing it on one blade. This just teaches you one more option here in the assembly. So I want to merge all of this into one part. The way to do that is through Boolean operations. So in the assembly module itself, if you look at the 4th row, it says merge or cut instances. So select the merge or cut instances. Give a name as merged part. Or merged blades. So we are merging by geometry. There is no mesh. We haven't meshed at all. So we're merging by geometry. Original instances we are suppressing, or you can delete it. It's up to you. I'm going to suppress it. And intersecting boundaries, I'm going to remove and continue. And it says select the instances to merge. Draw a box around all the 3 blades and say done. And now if you go to your assembly in the tree, you would see that all the parts are suppressed. You would see an X mark, they're all suppressed. Only merge blades is there. The merge blades is this entire instance, the three parts or the three blades are merged together into one part. You could, the same way you could cut, right? Boolean operation here we merged. You could do the similar to fiber reinforced composite. Say if you have fibers inside, so you model a cube and you cut that geometry out for the fiber. So that's the assembly merge or cut option. In case you need to use it for your project, you could think of using it. Is that okay so far? All right. So we will be, we'll take one of these blades and we will ask to create, we'll use extended finite element. The crack it has to generate wherever it is more stress concentrated. That's the location where the crack will start. But this is a complicated problem. We'll start off with tensile testing, crack propagation in tensile testing, and then we'll go to the wind turbine blade fracture mechanics. Is that okay? So you can save and close it. And we're going to learn some theory and then we'll do the tensile testing fracture mechanics first. So I have the sketch here. We can make the part for tensile testing. But first, let me introduce a few topics. So probably next class or Monday's class, we'll be doing the fracture mechanics on the wind turbine blade. All right, so some basic concepts I have not come across. If anyone has taken fracture mechanics or Professor Cortes has taught a fatigue and fracture mechanics course in the last term. If anyone has taken, that's fine. Otherwise, I'll give you some brief introduction to fracture mechanics. So we have three modes of fracture. Mode one, you can see a tensile load acting perpendicular to the crack surface. It's going to open up the crack. It's called opening mode, right? So tensile loading is extremely dangerous when it comes to cracks because it's going to open up the cracks. We call this as mode one. Mode one, this is universal concept, not just for Abaqus. Mode one means that's the type of loading. You have tensile load acting on the crack surface and the crack is going to propagate really fast. We call this as mode one or opening mode. This is the most dangerous mode, most common and dangerous mode of cracking. It's going to be the very first thing that's going to happen. That's because of tensile load here. The second mode, or the first mode itself, the displacement, if you observe the mode of deformation, if this is a crack surface, so if this is the crack surface, the displacement of crack surfaces are perpendicular to the plane of crack. So the plane of crack is the hashed region I have drawn. The displacement is in this direction. Displacement is perpendicular to this plane of crack, right? That's the most dangerous mode of cracking. It's called mode one. It's universal. Mode two is called sliding mode. You could imagine, say if this is the crack surface and say if you have a load acting in such a fashion that it's going to slide the crack surface. So the displacement of crack surfaces are parallel to the plane of crack. Previously, they were perpendicular to plane of crack. In sliding mode, the crack surface's displacement is parallel to the plane of crack and perpendicular to the leading edge. So leading edge, the terminology, what do we mean by leading edges? So that's the leading edge of the crack, right? Imagine this in 3D. So that's the leading edge. The displacement is perpendicular to the leading edge. So if this is the leading edge, the displacement is in this direction. perpendicular to the leading edge and parallel to the plane of crack. The hash region here is the plane of crack. That's called sliding mode. And usually, if you have sliding mode, it is there to alter the crack direction. So if you have sliding mode, the direction of the crack is going to change. And the third mode is called tearing mode or mode 3. Mode 3 or tearing mode is if you have load acting as if it's tearing of the two surfaces, or it's also called out of plane shear mode. Also called out of plane shear mode. The displacement of crack surfaces are parallel to plane of crack. Again, this is the plane of crack, the hashed region, and the displacement is still parallel to the plane of crack and also parallel to the leading edge. Leading edge is the front of the crack. That's the leading edge. So the displacement is parallel to this leading edge. We call it a tearing mode. Mode 1 is the most dangerous. So we're going to talk more about mode 1. It's most common and most dangerous. It happens because of tensile load. And generally, under an arbitrary loading, you would have mixed mode, meaning mode 1, mode 2, mode 3. Together, they will influence the direction in which the crack propagates. It's not just mode 1. Usually you have arbitrary shaped body with arbitrary loading. So you will have, so how do you take mixed mode? We're going to see some property coming from all three directions and equivalent loading we're going to look at. So that's the mixed mode. All three are responsible in order to find out in which direction the crack is going to propagate. Does that make sense? The three modes. So mode 1, mode 2, mode 3. There's a universal terminology, not just Abaqus. You will see this in Abaqus also, these three modes. All right, so crack. So crack is an amplifier of far field stress. What do we mean by that? So this is the crack, right? That's the crack. So you have far field stress. So somewhere here you have sigma, far away from the crack. Remote location, you have some stress sigma. That same sigma at the crack, it gets amplified, and that's the purpose of crack. That's what crack does. Crack acts as an amplifier of this far field stress sigma. And sharper the crack tip, higher will be the stresses at the crack tip. So if you have a blunt crack versus a sharp crack, this will have more amplification at the crack tip. So this will have more amplification than the blunt crack. So the sharp crack is very dangerous because of this amplification, you will reach that point of crack growth very quickly. Is that okay so far? What crack is? All right, so the stress intensity factor, the amplification of the far field stress is called stress intensity factor. Strength of the stress field in the vicinity of crack is called stress intensity factor. How much it is getting amplified at the crack, the stress intensity factor, that's what we're calling it. And each mode has a stress intensity factor, K1 for mode 1, K2 and K3. Each mode has a stress intensity factor. Right, K1 is for tensile loading or opening mode, K2 is the sliding mode, K3 is the tearing or out of plane mode stress intensity factor. And we just learned K1 is the mode 1 is the most dangerous mode when tensile loading is applied. So usually we have a very good empirical relation given by Erwin. Erwin for mode 1. For isotropic materials, the stress intensity factor for first mode is given by beta times sigma root pi a. The most important thing here is sigma. Sigma is the far field stress. So you have a load somewhere far away from the crack. You have sigma being applied, but the sigma is getting magnified by this term root pi a and beta. So sigma is the nominal stress that would exist if cracks were absent or far away from the crack. You have sigma being present. The sigma is getting multiplied with square root of pi a and beta, where a is called half the crack length for fully internal crack, and beta is called shape factor. I'll show you the simple formulas for this beta. Shape factor depends on geometry of your plate and the loading type, and beta is dimensionless. So that's Irwin's relation. It's going to predict, it's really good for isotropic materials, or especially for mode 1, which is the most dangerous mode. And so this is from textbook Cook and Young. As I said, beta is a shape factor. So K1 is beta sigma root pi for all of this different plates. So this particular plate has a crack, internal crack of length 2a. So this is internal crack. This is external crack or surface crack of length a. And again, this is a surface crack or edge crack with length a. All of them have rectangular cross section, and the difference is not just where the crack is present, also the loading. You have a tensile loading here, which is the most dangerous type of loading, right? You have tensile loading. We're talking about K1, that's why it's the for that mode, opening mode. You have stress intensity occurring at that internal crack. That's K1 beta sigma root pi. If you have an external crack, and because of the tensile loading, you have external crack and you have a moment. What does moment do? What does moment do? And why are we talking about moment when we're talking about mode 1 here? All of these formulas, you're talking about K1 here, which is the stress intensity factor. Stress intensity is how much the sigma is getting amplified. Even for the bending type of moment also, I'm talking about K1. Anyone? Why am I talking about K1 here for bending? Yes, Alex.
Bending applies the most blunt stress.
But what type of stress it applies? Bending? Yes. No, bending applies tensile and compressive, right? So imagine, I don't have the swans today. So imagine I'm bending it this way in the shape of a frowny shape. So you will have, if I imagine lines here, the top lines are stretching. There is tension on the top fibers. The bottom fibers are going to shrink. So there is compression. So bending moment is nothing but you have tension somewhere. So if you have bending moment in frowning shape, so you have tension like this, and the bottom surface have compression like this, right? So it's as if you're applying tensile load. That's why we're talking about K1 here, right? K1 is the for tensile loading for opening mode. So the topmost surface, if you have crack on the top surface and you're applying a bending load like this, the frowning shape, you have tensile load again at the top. So it's going to open up, that crack is going to open up. If the crack was here and I applied bending in this direction, the crack is not going to do anything. The crack is going to close. But because the crack is on the top and I'm bending it this way, I'll have tensile at the top. That's why I'm talking about K1 here. K1 is for opening mode because of tensile load. And K1 is stress intensity factor, the sigma, which is far field, getting multiplied with beta times sigma, beta root pi a. A here is the length of this crack. 2 times A is the internal crack length. A is the, so surface cracks are more dangerous, right? So only half the length is, if you have a big crack internally, that's not causing much damage here. Only half of it is going here. But if you have a surface or edge crack, that's far more, the entire length of the crack is getting magnified. So you have more amplification if it's an external crack. And the beta here, the beta is the only difference between all of these problems. So beta is given by this relation here. So beta is a function of geometry and also loading. So here A is the geometry of this crack. C is the geometry coming from the plate. and it varies, the beta formula varies if the external crack. And these are, and you can see the accuracy also, how accurately these predict, accurate to within 1% for all A by C ratios, accurate to within 1%, this particular formula, accurate to within 1%. So Irwin's formulas, they very accurately predict the K1 values using that relation and using the beta values based on the plate dimensions and the crack dimension and the loading. That's why we have three different formulas there. It's changing, beta is changing with the loading also. Is that okay so far? All right, so fracture toughness. So we would be entering all of this in our material properties. That's why we're going through this. So K1 is a stress intensity factor. It varies as per loading. You can see if sigma varies and wherever the crack is, it's going to vary. But that's not the material property that keeps changing as the loading changes, as the sigma changes. The material property that we enter in Abaqus is called fracture toughness. And we'll also enter one more material property called fracture energy. What is fracture toughness means? You would have done this if in your materials lab, a Charp impact test, ISOD impact test, similar, exactly the same thing, fracture toughness. What it means is you're measuring the energy absorption before fracture. If at all you have done the impact test, the Charp or ISOD impact test, you intentionally create a crack and then you fix it to a fixture and you drop a hammer, a swinging hammer will come and hit the crack, and the energy it absorbs before it completely cracks. You initially put a small crack of certain length and now you're hitting with a hammer, a swinging hammer. How much energy it absorbs before it completely fractures is called fracture toughness. The energy it absorbs before it completely failed is called fracture toughness, and it's a material property. I'm going to show you some value. As I'm saying, it's a material property. Steel will have some material property. Aluminum will have some material property, right? That's why it's a microstructure sensitive. It's a material parameter that can be obtained from experiments, and all the material database will have it. Microstructure sensitive. If you have marten stick or austenitic microstructure, it will vary based on the type of steel, right? 416 martensitic steel will have some other impact toughness or fracture toughness versus austenitic steel 304 will have some other. So it's microstructure sensitive. And this can also be interpreted as it is the critical stress intensity. Again, stress intensity is K1, K2, K3, right? It is the critical stress intensity or the maximum stress intensity at which pre-existing crack propagates. So if you already have a crack, the maximum amplitude, right? K1 is some sigma times some amplification factor. So the maximum value of this K1, K2 and K3, those are called as the fracture toughness, the critical values, and we use the C to denote that those are critical values. So each mode has a critical value. K1C is for the most dangerous mode, and these are listed in material database. MATLAB will have, or any material database will have K1C, K2C, second mode, third mode. They refer to the opening, sliding, and the tearing modes, the maximum values. And this is what we'll be entering in Abaqus. These are the material properties. Fracture toughness is the material property. We'll be entering it somewhere. And cracks propagate for mode 1 cracks. Cracks propagate when K1 is greater than or equal to K1C. K1 is given by Irwin's equation. I've just shown you the Irwin's equation here, right? For different loading, we have K1 is a function of beta. You can find the K1 value. And when this K1 is greater than or equal to K1C, the K1C is coming from material database. I have some examples here. The first mode K1C under tensile loading, steel can take only 175 megapascal, and those are the megapascal. a root meter, those are the units, right? The root meter is there for the units should make sense to you. So K1 is beta sigma root pi a, right? Beta is just dimensionless. Sigma has the units of megapascal. And the crack length, if it's mentioned in meters, that's the units megapascal square root of meters. And steel can have a maximum value of 175 before it can't have any more. It doesn't have any more capacity to hold on. It's going to propagate the crack. That amount of energy it can absorb, and beyond that it can't absorb. It's going to propagate the crack. And aluminum only 30. And titanium and so on. Glass is very brittle. You have a very small value. It can't absorb any energy at all. It's going to propagate crack throughout its length, right? That's the K1C, though. That's a material property. So if you have, so we're going to enter this K1C value in Abaqus. And whenever it's going to compute this K1 based on this sigma times some amplitude beta root pi a, whenever it reaches this K1C, the crack is going to propagate. Does it make sense? What's fracture toughness? It's a material property. We have one more material property called fracture energy. Again, this is material property. So this is the work done during fracture divided by surface area. So that's G is work done during fracture divided by surface area of fracture. So G, again, you have G is different in different modes. Fracture in mode 1 is G1F and so on, G2F, G3F. So for different modes, you have fracture energy. And again, this material property, you can find this in material database. Is that okay? All right, so XFEM. Let's see the time. So Abaqus has 3 different ways of modeling fracture. XFEM is the latest addition to, so we have 3 different modes. So I'm going to show you the 3 different options. In theory, we have 10 different ways of modeling fracture. Abaqus is allowing you to do it in 3 different ways. So the 3 different ways are contour integral method. So 3 ways to model fracture in Abaqus, and we'll be learning only one method, the best method we are learning. The first is contour integral method. The second method is VCCT, which is virtual crack closure technique. And the third method is XFEM, which is extended finite element method. I'll just point out where these are in Abaqus. But in theory, we have more than 3 methods. We'll be studying. Okay, let me show you where it is located. So if I go to interaction, say special, crack, create. So those are the 3 different methods of modeling fracture. One is contour integral method, XFEM, and the third is the debond using VCCT. VCCT is virtual crack closure technique, debond using VCCT. So those 3 are based on application, you would go for it. The contour integral method, the problem with contour, those are old methods, the contour integral and the debond using VCCT are old methods. XFEM is very recent, within last 10 years that has come, and very recently it's been introduced in Abaqus. So the reason why we are studying XFEM versus the other 2 methods is, in other 2 methods, you need to know which direction the crack propagates, and you need to create mesh in that direction. So for example, let me show you this picture. So this picture, if you observe carefully, let me make this bigger. If you observe carefully, I don't have any nodes or elements in this direction. It's going diagonally there. There's no edge there. XFEM can do this, whereas the other methods, contour integral method, debond using VCCT, I should know that. So if I have mesh only in that direction, it can go in that direction. Otherwise, the crack won't propagate. So I need to know beforehand which direction the crack is going to propagate. If I'm using the other method with XFEM, I can leave it to the solution in whichever way the stress or the strain criteria is met in that particular direction. Even if the mesh is not present, even if there is no element edge present, you can see it's going diagonally there. There's no element edge there, but it's able to propagate in that direction. And that's what XFEM allows. It's not, if you have good enough mesh, it can do this. It again depends on mesh. You need at least a decent mesh in order to be able to calculate the stresses and strains. And then it can be independent of the mesh. It doesn't have to have an edge in that direction for the crack to propagate. And that's why XFEM is the probably the best method for modeling cracks. Other methods have some advantages. The contour integral method is good for measuring the stress intensity factors. So these methods are good for stress intensity factors, measuring K1, K2, K3, right? And even the VCCT also. XFEM can still do this. We're going to find this K1, K2, K3. We're going to plot using our XFEM method. And we can also make the crack go independent of the mesh. So that's XFEM method. And there are more than this. In theory, we have more than this. Abaqus is not implementing this. ANSYS might have more than this. Is that okay so far? All right. The way Abaqus or XFEM, why is it so special? It's called extended finite element. So most of the softwares, they have problem with if you have a crack like this, you have discontinuity here, right? Say for example, look at the bottom edge of the crack. It has some displacement. The same node, it has one displacement. The top edge has another displacement. So you have a displacement jump, right? So you go from this edge, this node to this node. You have a displacement jump. Most of the other methods have difficulty in computing the displacement jump. And also at the crack tip, you have stress intensity amplification happening, right? And at the crack tip, exactly at the crack tip, you have singularity. So you have singularity here at the crack tip. So most of the other methods will have difficulty. How does XFEM able to do this? And it's independent of mesh. How does XFEM do this is through something called phantom nodes. So phantom nodes, we have two types of nodes now. All of you are familiar with the real nodes, right? If you mesh, those are going to be your real nodes. Phantom nodes are superposed on the real nodes. And these are the ones that are going to represent the discontinuity of the cracked elements. By that, what I mean is, so when you have elements intact, when elements are intact, when there is no crack going through the element, the phantom node is completely restrained to its real node. So each of these nodes have one phantom node and one real node overlapped at the same location. If the element is intact, if there is no crack. But when the element is cut through by a crack, so if the element is, say, for example, this particular element, so half of this element is here, half of this element is here. That particular element is now cut through by a crack. When that happens, now each phantom node and its corresponding real node can move away from each other. They don't need to be tied together. So you have phantom nodes and real nodes which are moving away. That's how the discontinuity is modeled. Say, for example, so this is the crack. So you have, so initially the crack is still not have separated this particular element. So this is the element we are talking about now. So the crack is going through it. We have at the same location, you have original nodes indicated as solid circles, and you have phantom nodes indicated as dotted circles. So the first picture here, I have the solid circle and the dotted circle overlapped. Whenever it meets the criteria I give, which is built by cohesive law. So I would give a cohesive law, and I would say the separation versus cohesive strength. So I'll be giving separation versus cohesive strength. So if at all it meets the criteria I give, this element is going to split into two. So that's the first part or the top part, and that's the bottom part. They can move independently because of these phantom nodes. So the phantom nodes say these are the bottom. The phantom nodes are with open circles, right, without any filling. So these were previously on top of these real nodes, and these top phantom nodes were actually overlapped on this top solid nodes. And now when they move, now they can move separately, the phantom nodes and the real nodes, if the criteria is met, which is given by cohesive law. Separation, so magnitude of separation is governed by the cohesive law until the cohesive strength of cracked elements is 0. So when the cohesive strength, cohesive means the adhesion, right? So when the cohesive strength goes to 0, the crack has completely gone through this element. And now that's the separation now between the real nodes and the, so that's the real node and that's the that's the real node and that's the phantom node. Now that's the separation we are deciding. So we are going to give a criteria for the cohesive strength to degrade and go all the way to 0. Cohesive strength of the cracked element will degrade and make it go to 0. So it has to meet some criteria. And when the cohesive strength of that element goes to 0, it's going to crack open. And the real nodes and phantom nodes can now move separately. Otherwise, the real nodes and phantom nodes will stay together. The crack will not cut through that element. And that's how the extended finite element method works. And if you have decent mesh size, if you have mesh size sufficiently refined, it has been proven that it doesn't exhibit any mesh dependence, which is what I was saying. So there is no elements along this crack direction. So there is no diagonal element here. It's going diagonally there. That's possible only with extended finite element method. With other methods, you would have to draw a line or a crack there or a partition. Only in that direction it would actually go. Whereas with extended finite element, it will figure out based on. So that's the next slide, I think. So the extended finite element method. So because of this phantom nodes, it generates and propagates crack through element where and when conditions are right. So we are not trying to create the direction for crack. It's going to, based on the solution, it's going to decide where the crack forms and how the crack should propagate based on the conditions, wherever the conditions are right. So we don't need to know where the crack starts and which way it propagates before analysis. It is part of the solution. So that's why extended finite element is really useful. And we just talked about phantom nodes. That's called enriched functions. So the presence of discontinuities are ensured by enriched functions, which are those phantom nodes. And they have additional degrees of freedom. So we have real nodes, which are the actual degrees of freedom. Now this enriched functions are nothing but the phantom nodes coming in. Those phantom nodes have additional degrees of freedom, and they are going to capture the discontinuities for me. By that, what do I mean is, how do we associate this phantom nodes in our displacement equation? Displacement is the one that is having problem, right? So if you remember, U is sigma ni ui that is N1 U1 plus N2 U2 plus so on, right? So what are these N's? Anyone remembers? U1, U2, U3 are nodal displacements. What are those N's? Anyone, do you remember this equation? U is sigma Ni Ui. We have a shape function for a truss element. We have a shape function for a beam element, right? Shape function for bar element or a truss element is, so N1 is 1 minus x by L and N2 is x by L, right? Or the other way. So those are the shape functions for a bar element or a truss element. Anyone remembers the shape function for a beam element? Or at least the order? Which order is it? In Abaqus also we have assigned it, the shape functions. This cubic formulation, right? Let me show you in Abaqus. So if you go to mesh, I don't have anything here, but let's see whether it allows me to do. So if I go to S4R, okay, there's nothing here. So let me open something. So beam, mesh, so S4R, S4R. So this is where we assign the shape functions, right? We have given cubic formulation. So N1 was some third order polynomial in terms of x, right? So cubic formulation was the, it's going to take Euler-Bernoulli shape function. Shear flexible is going to take Timoshenko shape functions. And what are the shape functions? Anyone remembers? What are the shape functions? Why are we calling this shape function? What is the other name for this N's? Why are they so important? Shape functions are also called. What are they doing from the nodes? They're interpolating, right? At any location you want. They're also called interpolation functions. The shape functions N's are also called interpolation functions because from the nodal displacement, you're trying to find displacement at any location you want. So that's the interpolation function. Shape function is how it varies from one node to another node. That's the polynomial for a beam. It varies cubically and so on. So that's core to finite element analysis, these shape functions. So that's why we have done some theory. We didn't completely focus on Abaqus. Otherwise, you will not know why we are doing these things. So shape functions are called interpolation functions. That's how the displacement is interpolated from the nodes to any location, intermediate location also we want. And if you have displacement discontinuity, you have convergence problems. The only way to overcome it is to manipulate that shape function. So you have, so that's your displacement here. U is summation of Ni times Ui. Now the displacement is some big function here. That's the shape functions. The shape function is getting multiplied by Ui, which is the same as previous case. Plus you have two more functions coming in. That's very easy to understand if I show that graphically. So you have two things happening when you have a crack here. You have at the crack surface, you have some jump. The jump is given by Heaviside function h of x. So when you're going from, so this node to this node, at the crack surface, you have a jump in the displacement function is given by the Heaviside function. That's this h of x. At the crack tip, you have singularity. So this singularity is taken care of using this f of x, f alpha of x. So f alpha x is applicable to nodes whose shape function support is cut by crack tip. So only these nodes in this pink region will have this f of x, and f of x is for isotropic. It's in terms of the radius of the crack tip and sine and cosine function. So that's the so Abaqus will know what to use at the crack tip region. It's going to use a sine and cosine and a function of the radius of the crack tip. So this f of x, capital F of x, is only in this pink region where there is crack tip. This h of x is throughout this crack surface, throughout this entire location. It's using this h of x, or Heaviside function is nothing but 1 and minus 1, right? Heaviside function you would have come across in math. So that's a jump. It's multiplied by ai, and the f of x is multiplied by bi. Those are coming from the phantom nodes. So these are the extra things coming. So these are for real nodes. Ui is for your real nodes. These are coming from the ai and bi are coming from your phantom nodes, which are phantom means imaginary, right? So you have extra nodes coming in. Those extra nodes are helping in explaining the discontinuity or the jump between the displacement from one side of the crack to the other side of the crack, and also the crack tip also singularity is captured by this. B is the enriched degree of freedom. So enriched degree of freedom vector and enriched degree of freedom here, both are for the phantom nodes. So the phantom nodes are inserted into your displacement equation through this function. So the shape function of your problem is getting multiplied by, you have two other terms coming in from the phantom nodes. Does that make sense? How the extended finite element method is working in Abaqus is the same concept in ANSYS also. If you use some other software also, the theory part is the same. If you are using extended finite element method is a technique, just like contour integral method or VCCT is a technique. So this part is same whichever software you use. So you have phantom nodes which have additional degrees of freedom, and those additional degrees of freedom will help in answering the discontinuity at the crack surface and also the singularity at the crack tip. Is that okay so far? So how is extended finite element independent of mesh? If you have mesh, what is mesh doing? When you write the input file, wherever the nodes are, it's going to store the nodal coordinates, right? So if you have opened an input file, wherever the mesh has nodes, those nodes are saved in the input file, right? But extended finite element, we are saying it's independent of the mesh. The mesh is represented only through nodes. We are saying here it's independent of mesh. So we have some other procedure in order to identify the crack geometry. So extended finite element has a different method called level set method. So it's called level set method. So instead of depending on nodes to define the geometry or define any part, extended finite element depends on something called level set method, which is used to describe the crack geometry, and that's why it's independent of the mesh, right? Let me open any part here, the beam part. When I open the input file, you would see where's the input file? So if I have all the parts are represented through these nodes, and the geometry is constructed by joining these nodes, that's how the bigger domain is broken down into smaller domains, right? So if you have used rectangular elements or triangular elements, those are assembled, the K matrix is getting assembled, the smaller domains are getting assembled to bigger domain only through these nodes, and the nodes and the x and y coordinates, if it's a 2D problem, 3D problem, x, y, z, three directions are there. We can't rely on these nodes anymore because the extended finite element method has to be independent of these nodes. It has to generate the direction and the location of crack by itself. That's why we have a method in extended finite element method to describe the crack geometry, and that's a pretty simple concept. How it does it? Through two signed functions, the crack geometry is defined by two orthogonal signed distance function. Signed means positive, negative. That's the sign we are talking about. So we have two distance functions which are orthogonal. They can have plus or minus. Those are nothing but your phi and psi. So the definition of phi. So if this is your crack surface, if that's your crack surface, the crack surface have phi equal to 0. And the surface orthogonal to it has psi equal to 0. So this is psi and that's phi. And we can output this in our output request. That's how we will keep track of crack. So phi equal to 0 defines the crack surface. Psi equal to 0 defines the orthogonal surface, which is perpendicular to the crack surface. Then the intersection, if you define these two, that's how phi and psi are defined. The intersection of these two surfaces will be your crack front, right? Two orthogonal surfaces intersection. That will be your crack front. And you have other notation, n plus and m plus. N plus is positive normal to crack surface. M plus is positive normal to crack front. So that's your n plus. The n plus is here. This positive normal to the crack surface. M plus is the positive normal to crack front. And then, so if you have this defined, the two signed distance functions are all you need per node to describe the crack geometry. What do we mean by that? Just with this phi and psi, you can locate all the other nodes. You don't need any explicit representation of boundaries or interfaces for crack. Only through these two functions, phi and psi, which are signed functions, meaning plus, and they can have plus or minus. I have an example to show you. So said that's my phi equal to 0 is the crack surface. So I'm looking at it perpendicular. So the crack is going into the paper here. The red region is the crack is going into the paper. That surface, crack surface is phi equal to 0. The surface perpendicular to the crack surface has psi equal to 0. That's our definition of phi equal to 0 and psi equal to 0, right? From the previous slide, this was in 3D. That's my phi equal to 0 surface. And this is my psi equal to 0 orthogonal surface. In 2D, that's going to look like this. That's my crack surface, and that's the orthogonal surface. Now, every node, say I have node 1, node 2, node 3, and node 4. How Abaqus or extended finite element keeps track of where the crack is, how it's propagating is. It's going to find the location of all the nodes surrounding it through the sign function phi and psi. For example, say if this distance is 0.5, say if this distance is 0.5, and say this distance is 1.5. How are these nodes 1, 2, 3, 4 calculated by this extended finite element method is? So any surface or any node above this crack surface will have positive phi value. So in this direction, I'm using phi. So if it's above this crack surface, I have positive phi. So node 1 and node 2 have plus 0.25. Any nodes which are below this crack surface, so if it is in this direction, they will have phi negative. So node 3 and node 4 have minus 0.25. Does that make sense? The total distance is 0.5. Above this crack surface, you have so positive values. Node 1 and node 2 have the positive values of phi. Node 3 and node 4 are below this crack surface, so they have negative values. Similarly, for psi, we have signs. How is node 1, node 2, node 3, node 4 is indicated through psi is on the side of crack, you have negative psi. So here psi is negative. So this is your psi equal to 0. Here psi is negative. Here psi is positive. To the right of the, or where there is no crack, you have psi positive. On the side of the crack, you have psi negative. So all of these nodes, 1, 2, 3, 4, are on the left side or on the side of the crack, right? This is psi equal to 0. All the 4 nodes are on this side, on the cracks side. So all of these have negative psi, and the distance from that psi equal to 0 surface. Node 1 is at a location of 1.5, so it has minus 1.5. Node 3 also, it is at a distance of 1.5 and it's minus because it's on the side of the crack. Node 2 and node 4 are at slightly shorter distance, so this is 1. So each is 0.5, you could assume. So node 4 and node 2 are at a distance of 1. They are negative because they are on the side of the crack. If the nodes, if I have a node somewhere here, then psi will be positive for that node. So that's how it identifies all the nodes through this signed functions, which is called level set method. So it's a very extensive method in math. It's used for many other things, not just for this extended finite element. You would hear this if you go to grad class. The level set method is nothing but you have some convention, the coordinate system now, phi equal to 0 and psi equal to 0. Based on this coordinate system, you are computing the nodal coordinates. That's how the crack geometry is always kept in track. So that it's going to calculate the nodal coordinates. It's going to update the crack based on this, right? Does it make sense? As the crack moves, the phi is equal to 0 surface also moves, psi equal to 0 surface also. We can actually ask Abaqus to display the phi value and psi value in Abaqus. So I'm going to show you where it is located. We'll be doing this in the next class. So if I go to step, I think in field output. So if you go to failure or fracture, so that's where you have phi LSM level set value phi and psi LSM level set value psi. Those two things are available to you. Those are the ones that are going to keep track of where the crack is. You ask it to display it, and they're going to display the crack for you. So phi LSM, the LSM is for level set method. Phi and psi are our phi represents the crack surface and psi represents the orthogonal surface. Does that make sense? So that's why the extended finite method element method is independent of mesh, because we have some other convention coming from the crack geometry itself. The crack geometry, one surface is phi equal to 0, the orthogonal surface is psi equal to 0. The coordinate system is defined based on the crack surface, making it independent of the mesh. Does that make sense? The extended finite element, how it's able to do this? All right, the crack initiation. So we need a criteria for crack to initiate. We need a criteria for crack to propagate. So that's what we'll discuss. And so far is common to all the softwares, not just Abaqus. From here onwards, we'll do it with the Abaqus example. So we'll be taking the tensile test example, and we'll do tensile test. So I have the, so we'll continue in the next class. So Abaqus fracture exercise 1. So that's the tensile testing I would do. And these are the things I'm explaining now. Damage initiation, what are those criteria? The stress values. You could use the strain criteria also, or principal stress, principal strain criteria. How do you decide the damage evolution? The crack needs to propagate, or the element loses the complete cohesive strength, so that it passes or cuts the element through. Damage evolution. If you observe the fracture energy, which is the G we discussed. So all of this will input in Abaqus. We will do the tensile test for 3 cases. We'll create a pre-existing crack. So the 3 cases we will do are, so just to understand fracture mechanics, we'll do 3 cases. Pre-existing crack, already some crack is present. And usually we do this for 2 cases, stationary crack. The reason why anyone does a pre-existing crack, that to a stationary crack, is to measure the stress intensity factors, to measure the stress intensity factors in mode 1, mode 2, mode 3. We're going to output this in Abaqus for the tensile test for a stationary crack. Means there is no crack growth. There is already a crack there. You applied some load. Tensile testing, you pull in one end, you constrain it to the lower crosshead. The other crosshead is moving. And at that crack tip, What are the K1, K2, K3? You're asking Abaqus to give. That's called stationary crack. The crack is not growing. Pre-existing stationary crack. You have an option to make it moving crack, meaning crack is propagating. When crack propagates, it's not going to output the K1, K2, K3. In that case, you're just interested in seeing in which direction the crack propagates, or already crack is located, pre-existing crack. So you already located it, in which direction it will propagate. That's the interest there. The second or the third case here, this is case 1, this is case 2. The third case is there is no pre-existing crack. So in our wind turbine, we have no clue. In tensile testing, we know, we have an idea. The crack will start in the gauge length, right? Usually when you don't want the sample to fracture in the fillet region or in the region where you're holding the tensile specimen in the crosshead, right? You want it to fail in the gauge region. So you have an idea where the stress is going to be maximum. It's in the gauge region because it's narrower compared to the other regions. The gauge region will have narrow cross section. So there, that's where you will put the pre-existing crack and you will find out the K1, K2, K3. But in your wind turbine case, there is no pre-existing, you have no clue where the crack is going to form. You're going to give some criteria for crack to start whenever the principal stress reaches a particular value or a principal strain reaches a particular value. It has to nucleate the crack. So it will nucleate as voids. All those voids join, and that's called coalescence of voids. They become crack, and that's how the crack propagates. And that's for the third case. All three cases we will do it for tensile testing. And the third case we'll do it for wind turbine. And the same material properties. I got this material properties from some Abaqus manual. We'll use the same material properties and we'll do it for wind turbine. So first we'll do it on this geometry to understand this. We'll go through all of this, the damage initiation criteria, damage evolution. In the next class, we'll stop here. If you have any questions on the project. So the project presentation is going to be next Wednesday, right? So you have, that's the last day of class. I will actually ask you your input. Do you want to present it in front of your colleagues, or you want to record a video and upload on Nexus? I'll send an email. I'll give you a couple of, I'll send an email tomorrow. I'll take a poll on Wednesday. And the majority, if majority of you wants to do it over Zoom, I mean recorded, I won't be present in Zoom. You're going to record your presentation. All you can open your Abaqus and present, or you create your PowerPoint slides. Whatever I'm looking for in the presentation, I'll send an email. I'm looking for introduction, then meshing, then the actual problem, objective, and so on. I'll send an email with whatever I'm looking for. You want to do it in front of your colleagues or as a recorded video? I'll take a poll on Wednesday, and based on that, we'll decide. Does that make sense? So if you have any questions on the project, I'll be here for 15-20 minutes. I'm available tomorrow also in office hours, 2 to 5:30. We'll stop here. We'll continue fracture mechanics next class, and also on Monday's class. Wind turbine might propagate to Monday's class. All right, we'll stop here.